Good morning, everyone. I, Andrew, Mohammed, Seif, Youssef, and Akram will present to you today our thesis defense for GPU accelerated data flow analysis supervised by Dr. Cherif Salama and Dr. Karim Ali. As you can see from the headlines, our world has witnessed a lot of software disasters. In fact, a small bug in your code can cost billions, and even worse, can cost lives. So here comes the role of data flow analysis. And actually, companies have been investing in program analyzers in general to avoid all this from the beginning. And this is the main topic of our thesis today. So what is data flow analysis? As the name suggests, it's basically analyzing your program by tracking the flow of the data along the program. So what might be the data? The data can be anything, for example, constants along the program, or even something more critical like in software security. Data analysis is about tracking confidential information. So for example, your password, and seeing if it got leaked to any malicious behavior in the code. So for example, data analysis will tell us that this simple code, we got here the password variable, got tainted into the variable B. So our thesis is about accelerating this data flow analysis. So why bother? Why would anyone want to accelerate this analysis? The problem is code bases is becoming huge. So imagine Microsoft's or Google code base. So in order to analyze a single program there, you will have a lot of dependencies to analyze too. And this made the analysis slower and slower over the years. Actually, this claim was documented in the literature by a survey conducted by Microsoft, where they interviewed software engineers and asked them what do they need or miss in current software analyzers. A lot of them reported that they were too slow and they wanted something to run in runtime and detect problems faster. So now we know the importance of data flow analysis and that we are going to accelerate it because we need to do so. And my colleague Zaieda will tell you how we are going to do that in our thesis.
So as my colleague has already suggested the reasons why to accelerate data flow analysis, here's how. Basically, we need to go into some theory at first. So if we can imagine a program that starts with this set of instructions, basically starting with the variable definition x is equal to 1, y is equal to 2, and simply deleting the value of x from the memory. And as you can see here, we can actually propagate the data facts of each variable at every execution of every instruction. And in fact, we can actually look at that as a matrix representation. So we can represent this data fact flow into a matrix representation. And in hindsight, this actually leads to our proposal of this thesis, which is simply trying to accelerate data flow analysis through GPU computation on the matrix representations. And the reason why we chose GPU is simply because it's friendly, meaning it computes matrix computations very efficiently. And as a first approach of actually attempting to look at that problem definition, we actually looked at current data flow analysis implementations and try to attempt to accelerate these data flow implementations in general. But before that, we actually laid down some metrics of choosing these implementations. Namely, we wanted to have a simple architecture for the sake of saving up the time of migrating this code base onto the GPU, which is already a hassle, and having a reproducible result, as we will later see that some of these frameworks do actually lack the fact that reproducing any results in general. And lastly, having the potential to be parallelizable on the GPU. Okay. And we'll touch upon that, how is that possible later on. And there are three main data flow analysis implementation that were explored, namely Phaser, GraphNG, and the LLVM data flow analysis framework. And after many exploration and research, this is basically the metric checklist that we had for each implementation. And as you can see here, that the Phaser, which is basically the state of the art of any data flow analysis at the moment, has the check for producing any results. However, it had a very complex architecture, which also led to having it, which lacked the opportunity to be parallelizable on the GPU. And the second, GraspNG, actually one of the few that had the potential to be parallelizable on GPU, since it was based on the GPU. However, it lacked the fact that it had reproducible results, and of course, having a simple architecture. And lastly, which is basically one of the most important of all, is the LLVM data flow analysis frame. And as you can see, it had a simple architecture, it had a reproducible result, and also it had some potential in being parallelizable on the GPU. And as my friend Andrew here will take you through regarding LLVM data flow analysis potential.
So how to parallelize LLVM data flow analysis? So first of all, it depends on the work list, which is a queue of functions to be analyzed. So first of all, the function will be analyzed using the compute data flow function till it finds a call site so that it will lead to a recursion to be fired. So our first approach to parallelize this implementation is to analyze functions in parallel, and the recursion was replaced with a recursion in the kernel. So there are two main challenges with this implementation. The first one is extensive usage of dynamic data structures, and the second one is the recursion in the kernel, which definitely slowed down our execution time. So our second approach is to use more GPU-compatible data structures, which was very hard due to the dependency on LLVM data representations, which was also dynamic. So our conclusion at that time that all the existing implementations are now parallelizable within our thesis scope. So we had to rethink and explore all possible paths. So we had two parallel paths at that time that we went through. The first path is a CPU multi-threading, and the second one is revisiting the literature in order to implement our matrix-based implementation to parallelize the data flow analysis. So our first path, which is the CPU parallelization, is almost the same as the GPU one, where every thread is responsible for analyzing a function to be analyzed. However, after having a pool of threads and implementing the locking and the unlocking techniques to protect the data, we had many runtime errors because of the highly dependency on the LLVM, which is not thread safe, which means they have functions and methods that are not protected against threads that use data at the same time. So leaving the floor to Seif in order to discuss the second path.
So let me introduce you to our matrix-based approach. So let me start with this simple x86 instruction. We actually have a system of four registers, EEX, EBX, ECX, and EDX. I'll just call them A, B, C, and D. So what happened here is we have some content or some data in A and D, and they being ordered and stored in EX. So as you can see here, there's some data flow or data leakage happened from A and D and stored in A. So let me introduce you to a fundamental concept in taint analysis, which is the taint state of instructions. So basically, both A and D, we can call them tainted because they had some data leakage or data flow. But B and C, they didn't have any data leakage or data flow. The content stayed the same. So that's why we can call A and D tainted. And the taint state of instructions or the taint state of the system is basically the information regarding whether a specific register is tainted or not. So taking what happened to another level, we can actually present what happened is in a system of linear equations, where on the left-hand side, you can see the output taint state of each register in our system. And it's actually a linear combination of all the input taint states of the registers in our system, having coefficients either 0 or 1. If we have a coefficient 1, meaning that the specific register has been tainted, and 0 otherwise. And the same goes for the rest of the equations. Taking it to another level, actually, we can represent the system of linear equation in a system of matrices, where we have the output state of each register in our system as a vector matrix, which equals to the matrix multiplication of the coefficient matrix, which we got from the system of linear equation, multiplied by a vector matrix of the input state of each register in our system. So what about the case with multiple instruction? It's actually pretty much the same. Imagine I had another instruction here, which is move EBX, EX, move the content of EX to EBX. What I need to do is I need to get a single coefficient matrix for each single instruction I have, and I need to do matrix multiplication with a specific order, placing the first instruction from the right, going through the left. And then what I should do is I should do matrix multiplication to get what's called the summarized matrix, which summarizes all the data flow facts that happen throughout the program. So the core operation here in the data flow analysis, or the matrix approach for the data flow analysis, is the matrix multiplication. So if we have a lot of instructions, for example, from I alpha to I omega minus 1, we can summarize their data flow as multiple matrix multiplication, as you can see here. And then we multiply it by the vector matrix we had for the input state. Then we can know some facts about what the data flow that happened. Now, my colleague Akram will walk you through the 3 stages of data flow analysis.
So basically, this brings us to our implementation. And in order to implement a full data flow analysis, we had 3 phases. First is convert x86 instructions into matrix, and then apply the matrix multiplication, and then at the end, analyze the results that we obtain. So for the first stage, converting x86 instruction to matrix, there is actually a taint-induced framework which takes an executable program as an input, and it results a matrix representation as an output of it. And this brings us to our second stage, which is applying the matrix multiplication. So for our implementation, we are considering a vector of matrices where each matrix is laid side by side of each matrix. And in our case, we will be considering 6 matrices. So the direct approach is to perform the sequential multiplication on GPU. So if we have the 6 matrices, we will be sending each 2 to the GPU to be computed, and then wait for the result in order to compute the rest of the results. However, this is very not efficient. So we had to find a better approach, which is multiplying each 2 threads, each 2 matrices in parallel on the GPU, which proven to finish the execution or to obtain the results in an iteration number of ceiling log 2 of m, where m is the number of matrices. However, since this will lead to thread diversion, which will affect the performance and will lead to performance degradation. So we looked at an optimized approach, which is making the first group of the matrices, or the threads responsible for the first half of the threads of the matrix, will be computing the results for the rest of the matrices. However, since matrix multiplication is not commutative, this will lead to it will lead to skewed results. So for our implementation, and actually we needed to prepare the input in order to finish execution efficiently, or avoid thread divergence, and also in order to obtain the correct result. So in order to do so, we needed to rearrange the input in order to make sure that each iteration will produce the correct output, and for the output of each iteration will be also prepared again, because it will be the input of the next state, and this will produce a correct results in a very in an efficient time. And my colleague Youssef will talk to you about the experimentation and results.
So the last part of our project was to experiment with our matrix multiplication approach and to test the validity of the GPU versus the CPU. The GPU we have used was Tesla T4 with a CUDA version of 12. And we had our 2 sets of experiments designed. The first set of experiments, we variated the sizes of the matrices multiplied And in the second set, we were variating the number of matrices to be multiplied. And in each set of experiments, we were testing this effect on 3 factors, the speed of the execution time and the gigafloating operating points per second for both the CPU versus the GPU. So as we can see here in the first set of experiments, we were fixating the number of matrices multiplied to be 32 matrices while changing their sizes to be up to 512 times 512 elements. And we were seeing this behavior on the speed up of the GPU that we can see here, a speed up of the GPU of up to 265x speed up compared to the CPU, while this is also reflected on the right graph on the execution times that we can see the CPU is increasing in its execution time while we increase the matrices sizes. The second set, we were fixating the sizes of the matrices to be 128 elements times 128 elements, while changing the number of matrices multiplied to be up to 1024 matrices multiplied together. And the speed up of the GPU is also increasing to reach a 125x speed up compared to the CPU, while also on the right subgraph, we can see the CPU is taking much execution time compared to the GPU approach. And finally, we also measured the G-flops per second for both the GPU and the CPU when we changed the size of the matrices and the number of matrices multiplied. And in each time, or in both graphs, the left and the right, we can see that GPU is having much larger G-flops per second compared to the CPU, which reflects that it can execute more or a larger number of instructions per second comparably to the CPU. And now with Basant to the concluding part.
So to conclude, the capstone empowerment outcome for our research, those are the main contributions through our research. The first one is that we reported on parallelization potential for different or the most popular implementations for data flow analysis. For example, Phaser, Grasp-ng, and LLVM data flow analysis, and provided the challenges that can be solved in later research in order to parallelize them. The second thing is that we dive deep in LLVM data flow analysis. We actually designed a framework to parallelize the work list, and we try to implement that on both GPU and CPU. And from all the challenges, we concluded actually good future work or potential project to actually make LLVM threat safe. And finally, we ended up by building our own matrix-based approach based on novel research that was published months ago. So we created or designed a pipeline for the analysis where we first take the executable and convert it into matrices, and then apply our vector of matrix multiplication implementation on the GPU. And actually we obtained a speed up to 250 times. So our next step is to actually document this main contribution and submit a paper to SEC conference in order to document our results. And thank you.